Ladies and gentlemen, it is time to talk about Chapter 11. This is fluids at rest, and or sometimes called flat static fluids. The first thing that we need to define here is called density. Density is a very simple concept. It is the mass per volume of a substance. It's how much stuff is crammed into how much area. And so you can see right here, this is the operative formula. Density equals mass divided by volume. Some books will use the D equals M over V like you see right here. Typically that rho is what we use. The Greek letter rho equals mass divided by volume. But whatever units you use, that's an important thing to do. Let's say that I take this one's a nice one down here. This is actually water. Right here, the density of water, and we'll see some other densities in just a second. But when they invented the metric system, what they did was they said we need to take the most common substance on the earth and make that the basis for measurement. So if you take a box that's 1 centimeter by 1 centimeter by 1 centimeter, and you fill that up with the most common substance on earth, water, then that would have a mass of 1 gram. Okay, so that's kind of where all this comes from. Therefore, the density of water is 1 gram per cubic centimeter. We can also call that 1 gram per cubic milliliter. A milliliter is a cubic centimeter, and so that would be another way to do that. But sometimes our favorite units are kilograms and cubic meters, and so you see here down at the bottom that 1 gram per cubic centimeter is the same thing as 1,000 kilograms per cubic meter. You could work that out if you wanted to do the unit conversions. I guess we could do it real quick here. 1 gram per cubic centimeter. I know that there are 1,000 grams in a kilogram. So we'll set that up to cancel out the grams right there. There are 100 centimeters in a meter, but you notice here that centimeters will not cancel cubic centimeters, right? So I'd really have to do that 3 times. I can either put an exponent up there to the 3rd power, or I could write it out 3 times, whichever way you like. I'll write it out 3 times just to make the point here. Okay, but now you can see that I've got centimeters times centimeters times centimeters would be cubic centimeters. That'll cancel the cubic centimeters down here. It would leave me with kilograms on top, and meters times meters times meters would be cubic meters. So we're thinking about a box that is 1 meter by 1 meter by 1 meter. If I take a box that big and fill it up with water, how much water would it have? Well, here I have 100 times 100 times 100. That would be this number, and I'm dividing by 1,000, so you knock off 3 zeros, and the density of water there would be 1,000 kilograms per cubic meter. Okay, so that would be the unit there. This is the important part, I guess, right here. Just remember that you have to convert those cubic centimeters to cubic meters, and that means you got to do it 1, 2, 3 times. So watch out for that. Here are a couple of examples, different ways that you can use the density formula. So this has a little bit of information that we can kind of play with and see how this works. Nothing tricky here though at all. In this problem, first problem here, they say that an oak beam, they give me the dimensions. It's 10 centimeters by 20 centimeters by 4 meters. And so the first thing that we did right here was to go through it and actually calculate the volume of that beam, of that board. So here's the 10 centimeters converted to meters, the 20 centimeters converted to meters. This already was in meters. When I multiply those together, this would be the volume of that board. Okay. Next, we know that our formula is density equals mass divided by volume. They told me that I had a mass of 58 kilograms, so we've put that up top. I've got the volume that we found there on the bottom, and therefore the density of this board is 0.725 grams per cubic centimeter, or 725 kilograms per cubic meter, either one. Notice that I can just move the decimal place 3 times. That's that 1,000 that we had on the last screen. So that's a useful thing to be able to do right there, to find the density of something. We said earlier that the density of water was 1,000 kilograms per cubic meter. This has a density of 725 kilograms per cubic meter. So therefore, my board has a lower density than the water, and if I threw this board into water, it would float. Something that has a lower density than water will float. Something that has a heavier density will sink. So that's one direction this can go. Before we do that, here's another problem at the bottom, and on this one they say that I've got a lion with a mass of 250 kilograms, and here the density is equal to water. So we're just assuming that that's 1,000 kilograms per cubic meter, and we've put that in there for the density. We did a swappy thing on that. 250 right here. That would be the volume of the lion. It would take 4 lions to fill up a box that's 1 meter by 1 meter by 1 meter. Okay, I don't know how you're going to get them in the box. All right, use some gloves, I guess. So here is a table, and there's a table kind of like this in your book that has some densities. These are broken down into solids, liquids, and gases, and so you can see here that wood can vary anywhere from 0.3 to 0.9 grams per cubic centimeter. There actually are some woods that are more dense than water and that do sink. They're kind of exotic woods though, and so most of them will float. Ice is a little bit less than water. That makes sense, because if you throw an ice cube into a glass of water, it floats, right? Aluminum here is a nice one, 2.7 grams per cubic centimeter. Iron, steel is about 7.8. Cu stands for copper. That's the chemical symbol for copper. This would be lead, and down here is gold. So some different metals, but you can see that these things vary. Aluminum is very lightweight, 2.7. The gold is 19.3. Lead is pretty heavy stuff, but gold's even heavier than lead. So it's really easy to go through and see what the densities of these materials are and how heavy they'll be for a given size of that material. Liquids are in the other box here. We've already talked about water. Seawater right here is a little bit more dense than regular water. So that's interesting. There is also a liquid called mercury. We don't get to play with this anymore. Sadly, they've discovered that it's dangerous, toxic, so we don't break thermometers and play with it in our hands anymore like we used to do when I was a kid. But 13.6 grams per cubic centimeter. That is a heavy liquid. That's some dense liquid right there. If you were to take a bucket of mercury and throw nails into it, throw a blacksmith anvil into it, throw anything that's steel, a hammerhead or something, it would float. Chunk of steel would float right there in the mercury. How do we know? The density of mercury is 13.6. The density of iron and steel is 7.8. Iron has a lower density, so it's going to float in the mercury. That's pretty crazy. I could actually float lead, 11.3. I can't float gold. Gold would sink, but the lead would float in the mercury as well. So you got to look at the density numbers. On the gases at the bottom, you can see these are very small numbers, right? 0.179 grams per cubic centimeter. Air, this is an important one here, 1.29 grams per cubic centimeter. And so things vary differently. Right here, this steam, that's effectively water, right? So here's a version of water. Here's liquid water right here. Here's a gas form of water, and then over here with the ice, I've got the solid form. So I've got all three forms of water there, and you can see that the most dense of them would be the liquid water. That's kind of interesting. Steam is less dense and the solid is less dense. You know that if you've ever put a bottle of water in the freezer, as it freezes, then it expands. It gets bigger, and you can break the bottle and make a big mess in your freezer if you're not careful. So watch out, a jar of soup or something. Be careful with that. All right, here's the next little thing called specific gravity. Very simple idea. If I take the density of a substance, like any of those that I was just talking about, and I divide by the density of water, then I end up with this number called the specific gravity. And so we've done one of these here. If I wanted to calculate the specific gravity of lead, then I could look it up on the table. 11,300 kilograms per cubic meter. Before we had grams per cubic centimeter. That would work too. We could come in here and say, where's my pen? 11.3 grams per cubic centimeter. Divide by the density of water in those same units. So I could use 1,000 kilograms per cubic meter. Just make these units match those units. Over here I'd have to do 1 gram per cubic centimeter. Either way I do it, I get 11.3, right? That's a way to say that lead is 11.3 times more dense than water is. We're using water as the reference. We're saying lead is 11 times more dense than that. And you could see how you could do that with any of those materials. All right. The next thing here we want to talk about is pressure. Pressure is force over area. It's the ratio of the force on an object to the area over which the force is distributed. So we've drawn a little picture here of a, could be a board, could be anything, and there are forces that are pushing down over that, spread out over the area of the board, and the amount of force per area determines how much pressure there is. Now, usually we think about air pressure, right? Atmospheric pressure. We're going to talk about that some, but it works the same way. If I come in here and I draw, I don't know, here's my head, okay? And their air is pressing on my head, right? And everywhere over the whole surface area of my head, there's pressure there. Well, it's force. It's force over that area, and so I could calculate the amount of air pressure that I have there, or I could look it up or something. Since we talk about force over area, the units of force would be newtons. The area should be measured in square meters, and we end up with this unit, 1 Newton per meter squared. We call that a Pascal. Blaise Pascal was the guy that worked a bunch of this stuff out, so we named it after him. A Pascal is a Newton per meter squared, and we can just work that out and see what how many pascals we get there. But you should know that there are lots of other units of pressure. People have done so many different things with pressure. The guy at the filling station is filling your tire. He's working in PSI. That stands for pounds per square inch. So you can see there again how the pounds would be force, square inches would be area, so that's a measurement of force per area or pressure. And anytime you have 1 psi, that'd be 1 pound per square inch, like we said, 144 pounds per square foot. I can also get back to atmospheric pressure. If I have 14.7 psi, that's what we usually record as atmospheric pressure. So the air pressure on average is something like 14.7 psi. Well, that's equal to 1.013 times 10 to the 5th Pascal. So lots of options there. If I take that 10 to the 5th Pascal, somebody thought they'd be cute and call that a bar, right? So a bar is a unit of pressure. 1 bar is equal to 10 to the 5th Pascal. I could have a millibar. That'd be 1,000th of one of these things. So that'd be 10 to the 2nd, or 100 Pascal. The blood pressure people, you know, the nurses and stuff measuring your blood pressure used to work in torr. Well, 1 torr is equal to 133 Pascal. So because there are so many different things that you can do with pressure, there are a lot of different units. Our favorite unit, though, is the Pascal, where 1 Pascal equals 1 Newton per meter squared. And that's just the easiest thing to do. But lots of other options out there on this thing. The weather people, for example, used to measure in millimeters of mercury or millimeters of water, right? They had a tube, and they would fill it up with water and then turn it upside down and put it into a bowl of the same liquid, and that liquid would fill the column up to some height, right? So my column of the height is from the water level in the bowl up to the top of the column height, and you measure that height right there. That is a way to measure the air pressure. What's happening here is gravity is trying to pull all of this down, and the air pressure is pushing down on this bowl, forcing fluid back up. So it's kind of a battle to see who wins, gravity or air pressure. When air pressure increases, then it pushes harder, and I get a little more fluid in here. When air pressure decreases, it's not pushing as hard down on the bowl right here, so my water level would fall, and I would have, you know, falling air pressure. That usually indicates a storm coming, either rain or wind or something. So, you know, the barometer like this has been important for predicting weather. But millimeters of mercury, if you take mercury and fill this thing up and you measure up the height in millimeters, then that's another use of pressure. All right. Let me tell you about 2 different kinds of pressure here. There are lots of pressure gauges, like the one that you see at the left bottom here. The gauge measures what we call gauge pressure, and the gauge pressure would be whatever it reads over and above atmospheric pressure. So on this little gauge right here, you can see that the black numbers on the outside are PSI. So this is like 8 PSI. That means it's 8 PSI over and above atmospheric pressure. So you'd have to come in here and say my gauge pressure. My gauge says 8 PSI, but I know that atmospheric pressure is something like 14.7 PSI on average. And so I'd really have to add those 2 together to get what we call the absolute pressure. So those would be, that's a little bit confusing, especially since books aren't all that good at saying which one they're giving you. Sometimes it'll be a gauge pressure, sometimes an absolute pressure. But if your answer doesn't work out, then try it like that. The gauge pressure is what the gauge says. The atmospheric pressure is the pressure of the air. And when I add those 2 together, I've got my absolute pressure. Another way of thinking about this is if I took this tank that's reading 8 PSI here on Earth and I took it up to space, right, then the 8 PSI is the difference between inside the tank and outside the tank. If I take it out into space, there's 0 pressure outside. So now I've got 8 pounds per square inch above Earth's atmosphere, but that's 14.7 PSI above space's pressure, so there's an absolute pressure there at 22.7. Okay. Here's another use of pressure. Pressure at a depth. The deeper I go down, if you've ever swam down into a pool, you know that the deeper that you go, the more it presses on you, and you can feel that most acutely in your ears. Your eardrums are made to measure pressure, to sense pressure differences. When I speak, pressure waves go out, and that your eardrums pick up that change in pressure and rub some bones together, and that rubs on a nerve, and somehow you hear. Not really sure how that works. Go talk to the biology people. But the deeper down you swim, then the more pressure that you have. Let's say I swam all the way down to here. This is kind of a little swimming pool. but I'm going to jump in here and I swim down. We usually use H for the depth, and again that's measured from the water level down to where I am, and I measure that depth right there. Let's say that I swim down 4 meters. The idea here is that I have all of this water stacked up on top of me, and gravity is pulling that down, so I've got to hold the weight of that water up. The deeper I go, the more water I have stacked on me, so I have more water pushing on me. Does that make sense? Here's all you have to do to calculate the pressure at a depth. If you take the density of the fluid, multiply by G, and then multiply by the depth, it looks like that. So really easy to do. We said we were going to swim down 4 meters, so I could come in here and say my density times G times H. Use the D, use the rho, I don't care. My density of water is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. Trying to squeeze this in, didn't do very well here. And I swim down to 4 meters. So all I have to do is to grab my calculator and go 1,000 times 9.8 times 4. And there's the number, 39,200. Let's take that back and see what the units would be. When I look at the units that I have, I've got a kilogram and a meter per second squared, and then here's another meter, and then it's all over cubic meters. So what we want to do here is to lump some of these together, and here specifically, if I take that kilogram meter per second squared, take that much of it, that would be a Newton. I'd have a meter right there, that's over meters cubed. This meter would cancel one of those meters, so that leaves me newtons per meter squared. A Newton per meter squared is a Pascal. If I swim down 4 meters, then I will have a pressure of 39,200 pascals. Pascal's not a whole lot of pressure, right? Because remember, it was force divided by area. If I take 1 Newton, spread it out over 1 square meter, a Newton's like 100 gram mass in your hand, right? Not much at all. Spread that out over a table that's 1 square meter. That's a little bitty unit of pressure, so you're going to have a whole bunch of these to do any kind of thing. And right there's that number. This, though, is the gauge pressure. This is how you calculate the gauge pressure at a depth. If a scuba diver goes down to the bottom of Lake Murray, or 4 meters down, then his gauge would say 39,200 Pascal. He's probably in different units, but whatever. If he wanted to know the absolute pressure, then he would have to come along and add the atmospheric pressure, and you remember that was plus 101,300 Pascal, and he'd get the total there, 140,500, something like that. Okay, so this gives you the gauge pressure. Next up, we've got the buoyancy principle. The idea here is that anything that displaces a fluid gets a little bit of help. It gets a little bit of upward force here. I've put the guy here floating above his desk. That's kind of silly. Maybe a better example would be something floating in fluid. So let's take a bucket of water here, and I'd like to throw a little rubber ducky into it. Right there. And we fully expect the rubber ducky to float unless it's full of water or concrete or something. So something is pushing that thing up. I certainly have the weight, mg, pulling down on the rubber ducky, but something is canceling that out and making it so that it doesn't sink. We call that something the buoyant force, and we usually mark it F sub B, like you see right there. So how do we calculate that? How do we do floating problems? Whether it's the rubber ducky floating on the water, whether it's the guy floating above his desk, or more realistically a balloon or a blimp floating in the air, how do those kinds of problems work? That's pretty easy. The buoyant force is equal to the weight of the fluid that's displaced by the object. When I look at the rubber ducky problem, I only get to count the fluid that's displaced, right? That's the part of the rubber duck that's underwater. So I only get to count that much of it, and that would be my displaced volume. Because the rubber ducky pushes on the water, Newton's third law says every action equal and opposite reaction, right? If the duck is pushing on the water, then the water is pushing back on the duck, and I get that upward force right there. So there's one way to think about it. The other way to think about it is if I have an object in water, then the pressure at this point at the water surface is one number. The gauge pressure would be effectively zero because the depth below the surface of the water is zero. As I go down, I have more pressure. So here I have a greater pressure. Pressure is force over area, so I would have more force on the bottom, and I get that little upward push because it has more pressure on the bottom of the rubber duck than it does on the top. Okay, so either way you want to think about it is fine. But this is the way you calculate it down here. The buoyant force is equal to the density of the fluid times the, this should say the displaced volume. Okay, if the whole thing were underwater, then it would be the volume of the object. Or if it's the guy sitting at his desk, right, then all of him is displacing air. But let's change that V sub object to V sub displaced, just to make sure that we're only counting the part of the object that's displacing the fluid. It's only the bottom part of the rubber duck, and for the guy here it would be all of him because he is completely submerged in air. All right, and then multiply by G. Let's do one of these real quick. These are kind of fun to do. Let's say that a log has let's see, how do we want to do this? I could just give you the volume. Let's say 0.8 cubic meters underwater. That's just the part underwater. So then if I want to find the buoyant force, F sub B, then I could come in here and say, well, I know F sub B equals the density of the fluid, not the density of the log, it's the density of the fluid, times G times the displaced volume. So when I put those numbers in, the fluid is water. Water has a density of 1,000 kilograms per cubic meter. G, 9.8 meter per second squared. And the displaced volume here is 0.8 cubic meters. These cubic meters cancel those cubic meters. That would leave me with kilogram meter per second squared, which is a Newton. And then here I have 1,000 times 9.8. That would be about 10,000. 80% of that would be about 8,000. We can get a better number, I guess. Let's go here and we'll say 1,000 times 9.8 times 0.8, 7,840. That's pretty close to 8,000. So 7,840 newtons. Okay, remember that a newton's not a real big unit of force, so that looks like a huge upward force, but I've got to do something else. Here's the log, and I've got this buoyant force that we just calculated, 7,840 newtons. I also have to consider the weight of the log. If the weight is greater than the buoyant force, then the log is going to sink. If the buoyant force is greater than the weight, the log will rise. If they're exactly equal, then they cancel out and it stays there. So what we need to do is to come in and sum the forces and set it equal to the mass times the acceleration. We use Newton's law on it here, and every one of these, if you'll just draw this little picture and think about the forces that are acting on it, set that equal to mass times acceleration, and then solve the problem. Right here in my picture I have two forces, so I would do F sub B minus mg equals ma, and that's my problem, right? We already know what the, not sure where this problem will take us here, but 7,840 newtons. A lot of times if the log is just floating, right, if it's static, then the acceleration would be equal to 0, so this would cross off right there, and I could add mg to both sides, and I know what g is, so then I could find the mass of the log. And so here I could come in and say 7,840 newtons, divide that by 9.8, almost 10, somewhere around 780, let's call it 790 kilograms right there for you know, the mass of my log. So these equations, you know, a real simple equation. We've done this over and over right there, but that's all you have to do for the buoyancy problems. Here's another one. Let's say that I have a steel anchor is suspended underwater. Tell you what, let's go with seawater this time. By a rope. And let's say that the anchor has a mass of 60 kilograms. Pretty good size anchor. All right. What we would like to do here is to find the tension in the rope. Okay. So, like always, first thing would be to draw a picture. Here's my water level. The anchor is completely underwater. So we'll come in here and we'll draw the anchor underwater, and it looks like that. Next, I need to think about the forces that are acting on my anchor, and of course we know that weight pulls straight down. Gravity is trying to pull that anchor to the bottom of the ocean. I've got a rope, we'll call that T, and then I've also got this buoyant force that helps push it up. There are three forces on the anchor. Gravity is pulling down, the rope is pulling up, the buoyant force is pushing up, right? And here again, the bottom of the anchor has more pressure than the top of the anchor. More pressure means more force per area. I get an upward force there. So even though it's completely underwater, those would be the three forces that I need to put into this picture. As always, I go sum of the forces equals mass times acceleration. Here I have three forces, T, F sub B, and mg. That's equal to mass times acceleration. This thing is suspended, so I'm going to assume that it's just hanging there. It's not going up, it's not going down, and let's say that the acceleration equals 0. All right. What I want to find is the tension in the rope. So I want to solve this thing for T. I do need to get my signs in there. So I come over here, create a little coordinate system, and one direction needs to be one sign and the other direction the other sign. Let's call up positive, down negative. The tension is up, the buoyant force is up, the weight is down, so I've got plus plus minus on my signs there. If I'm trying to solve for the tension, that's pretty easy. I will add mg to both sides and subtract F sub B, and I get a thing like that. Let's see where this takes us. Mg minus, I know that the buoyant force is the density of the fluid times G times the displaced volume. It would look like that. Let's stop here, and not stop here, but let's pause here, see what we have. I know that the mass is 60 kilograms, so I have that. I have G. This is seawater, right? And the table had that the density of seawater was a little bit more than the density of water. Water was 1,000 kilograms per cubic meter. I think 1,025 was the number for seawater there. Why don't we use that? I may be a little bit off. I don't care. Density of the fluid, I have that. I have G, so I'm almost good here, but I don't have the volume of the anchor. They didn't give me that in the problem, and it seems like I'm stuck. I don't know T, and I don't know the displaced volume. So anytime you get stuck in one of these problems, what you got to do is say, okay, I want to think about the anchor, and for the anchor, the density of the anchor is equal to the mass of the anchor divided by the volume of the anchor. And you can see where this is going. I want the volume of the anchor, right? In this case, the displaced volume is equal to the anchor volume because the whole thing's underwater, right? All of it is displacing fluid, not just part of it. All of it's underwater. So if I can find the volume of the anchor, that would be my displaced volume. Do a swappy thing here. The volume of the anchor is equal to the mass of the anchor divided by the density of the anchor. The mass of the anchor was 60 kilograms. The density of the anchor, well, they told me it was steel, right? So I got to go to the table and look up the density of steel, but I believe that was 7,800 kilograms per cubic meter, and see how I can get the volume of the anchor. I have this number now. Okay, so I want to put that in numbers here. I've got 60 kilograms times 9.8 meter per second squared minus the density of the fluid, that's my seawater, 1,025 kilograms per cubic meter times 9.8 meter per second squared, and then my displaced volume is whatever that came up to. I'm going to just put it all here, 60 divided by 7,800, and we'll punch it all up at once and get a number out of this thing. But that would be the tension in my rope. Let's see what we get. I've got the 60 kilogram anchor, 9.8 is gravity, and then I want to subtract the density of seawater times G, and then times the volume of the anchor. That was 60 divided by 7,800, and there's my equation. 511 newtons is what we get out of that. For the tension in the rope. Okay. If this thing were not underwater, you see how I wouldn't get the help from the buoyant force? This is the buoyant force right there. As soon as I pull that anchor out of water, or maybe this is a fish, if you're a fisherman, then you know that you can catch a fish and you reel it in closer and closer, but you don't just reel it up out of the water, right? You get a net and get underneath it and stuff. Why? Because you're going to lose that help from the buoyant force, which puts more tension on your line. In this case right here, if I didn't have the buoyant force, then my string would have to hold 60 times 9.8. It would have to hold 588 newtons, right? But as it is, I've got some help there, 588 newtons. Okay, so that's the help that it gave me there. Again, your fish, could easily break the line if you're pulling it up straight out of the water with the thing. All right, last topic here. This is the idea of hydraulics. This is kind of the last part of of fluid statics. I've got a couple pictures over here of hydraulics. I've got a little jack like this. This little red jack is a handy thing. You can roll it up under a car, and then you can pick your car up with one hand. All right? You take the handle here, you stick it into the end of this thing, and then you're going to pump it up and down, and this arm right here is going to go up, and it's going to lift your car. I push down a little bit over here, a small force there, and I get a big force up right here, enough to lift a car. I can't lift a car with one hand, but with the jack I can, so that's kind of neat. At the bottom you've got a dump truck, and we're looking here at this thing. This is the hydraulic cylinder that we're interested in, and it works off of the same principle as the hydraulic jack that you see at the top up there. The picture over on the right hand side is what I'd like you to look at, though. The way this thing works, the way it multiplies your force, is you have two cylinders. One is a relatively small cylinder, and it has a cross-sectional area right there, that light gray oval or circle of A1. Over here I've got a bigger cylinder, and it has a larger cross-sectional area, gray circle there, and that area would be A2. Again, what I want to do is to push down a little bit on this side and have this thing multiply my force so that I get a big force up. So little force here, big force there, because I have a little cross-sectional area here and a big cross-sectional area right there. The way this works is on the next slide here, and what I want you to remember is that the pressure at side 1's got to be equal to the pressure at side 2. If I have a dot right here and a dot right there, if I pick 2 points that are at the same level, then I could find the pressure at point 1 and the pressure at point 2. Those have to be the same number because this is fluid, right? The fluid can move. If I had high pressure at point 1, for example, then the fluid would move and equalize. It would come out, and pressure 2 would be the same. So that's where I want to start on this thing. Pressure 1 equals pressure 2, and pressure, of course, is force over area. So I've got pressure 1 is force 1 divided by area 1. Pressure 2 is force 2 divided by area 2, and I end up with this really nice equation that ties together how much force I can expect to get out of this thing. I put a little force in, I get a multiplication of force that helps me lift big heavy things. Here's an example. Let's say that my cross-sectional area on side 1 is 4 square centimeters. The units don't really matter here. Use anything you like. Let's say that this one goes up to 20 square centimeters. So I've got A1, I've got A2, and then maybe I push down with 100 newtons here, and let's see what happens when I work this thing out. I want to solve for F2, so I'll multiply both sides by A2. That would give me F1A2 over A1 equals F2. Force 1 here was 100 newtons. A2 is 20 square centimeters. A1 was 4 square centimeters. The square centimeters cancel out. That's what I was saying about the units didn't really matter. If you convert one, then you're going to convert the other, and all the conversions cancel out too. 4 would go into 25 times. 5 times 100 would be 500 newtons. I just made myself 5 times stronger here. I push down with 100 newtons. I get 500 newtons out. Now, you know enough physics and conservation of energy to know that we do not get that for free. You don't get anything for free in this universe. So how do we pay for that thing? Well, what has to happen here is the piston that I have right here, when I push down, that piston is going to move a certain distance. Let's say it goes down there, and we're going to call that distance L1, the length that the piston moves. And then I've got a piston over here, and it's going to go up some distance, and we're going to call that L2. The trick to doing this is to realize that the volume of fluid that I move on side 1 has got to be equal to the volume of the fluid that I move on side 2. And so if I set those two equal to each other, volume 1 equals volume 2, the volume of fluid that I move right there would be equal to A1L1. This volume right here is the cross-sectional area times the distance that it moves, A2L2. So that thing, this right here, relates the cross-sectional area and how far those pistons have to move to make this happen. All right, so here again, maybe L1 equals 40 centimeters. I push it down 40 centimeters. How far up does it go over here? And all we got to do is solve for L2. That would be A1L1 divided by A2. So there I've got 4 square centimeters times its distance, 40 centimeters, and then I'm dividing by 20 centimeters squared. The centimeters squared cancel out. 4 goes into 25 times 40 divided by 5 would be 8 centimeters. Okay? I push my side down 40 centimeters. The car only goes up 8 centimeters. So that's why we have to pump that handle over and over to get the car up high enough to get under it to work on it, or to take the tire off, or whatever we're doing like that. That's fluid statics. We'll do some more of these problems in class, but that's what you need to know. So thank you very much.